My name is Jim Murphy. I serve as the director of the X-ray Crystallization Core Laboratory at the Yale School of Medicine. Today I'd like to discuss the value of automating portions of a protein crystallography pipeline and the application of automation in an academic setting. I will also discuss instrumentation in our core laboratory and how it can be successfully integrated into a structure-based scientific project. Protein crystallography and the subsequent atomic level structural determination of biologically relevant macromolecules has significantly aided the understanding of human disease at the molecular level. As the knowledge of accurate molecular structures is a prerequisite for rational drug design, protein crystallography has also had a substantial impact on the drug discovery pipeline. Here we see a representation of the workflow pipeline of a typical academic research structure biology discovery project, beginning with a scientific inquiry and hypothesis and a choice of target, usually accompanied by granting and funding. Then through the often difficult process of laboratory work of purifying protein, then the bottleneck step of obtaining crystables suitable for obtaining high-resolution structural data, and then through the computational process of structure solution, and finally publication. So today we'll be focusing on that bottleneck step of obtaining high-quality crystals using automation and protocols that are applicable to small or medium-sized laboratories to improve the often tedious process of the high-throughput steps of condition screening and optimization and imaging and data management. While there are structural biology research groups, most notably the Structural Genomics Consortium, and previously the Joint Center for Structural Genomics of the Protein Structure Initiative, this is not what this seminar is about. We'll be focusing on what we can do on an academic scale. Their primary purpose is completely automated crystallography, developing intense, fully automated pipelines that optimize high throughput of every step of the process, from cloning to protein expression to data collection and structure solution, going after numerous targets, often without a specific targeted scientific rationale. They employ large budgets, they have lots of personnel, and tremendous amounts of equipment. And they're producing structural data at a rapid pace. And more importantly, in our case, they're pushing the limits of automation and developing ideas that can be implemented in a smaller, more targeted structural biology research laboratory, such as in our case. So the focus of today is working in an academic environment. Typically, these are scientific projects that are very focused on fewer specific biological targets, as well as in an environment which values learning and the training of research scientists. So typically our core has researchers whose goals can be divided into two classes. The first class are high-impact targets. They've not been previously crystallized, where often the first goal is simply getting to that initial crystallization hit as efficiently as possible. And the second class is a target which is well-studied, the crystallization conditions are known, and the projects involve a series of mutations and complexes with bound small molecule ligands. And of course, always keeping the end goal in focus, which is the determination of the atomic structure of the target as part of the greater research environment, as that is where the scientific discovery lies. So which parts of the pipeline can we optimize? The design, setup, and imaging of crystallization growth. So by automating parts of a traditionally tedious and time-consuming process. So what I'll be covering in more detail is the experimental setup using some integrated software, experimental setup itself using a robotic liquid handler, the MT8, imaging using a robotic imager, the RI1000, and also image analysis using integrated software. And then repeating this process, bootstrapping up until crystals suitable for high-resolution diffraction are obtained. Next, I will discuss several of the robotic instruments used in the automation of your crystallization pipeline. First is the Formulatrix MT8 Drop Setter. The MT8 is a robust liquid handling instrument for drop making and crystallization screen preparation. We can use any plate that has a standard 96 well Society for Biomolecular Sciences, or SBS, microplate footprint, and can set any type of crystallization experiment, including vapor diffusion, hanging drop, sitting drop, under oil, additive screens, seeding, grid screen hit optimization, or anything else that you'd like. To get the most out of a protein preparation, which is typically time-consuming and expensive to make and often the limiting reagent in the experiment, minimizing the volumes of the crystallization drops is important. This requires automated liquid dispensing methods that are capable of accurately dispensing very small volumes of liquid with a wide variety of surface properties and viscosity. The MT8 can handle volume as low as 50 nanoliters. Precise, accurate, and consistent drop setting is crucial for both projects that require an initial hit to be followed up on, and also for higher throughput projects where we're looking at multiple protein variant and or multiple bound ligands. So let's take a look now at the MT8 in action. This is the MT8 Drop Setter in action. What we're doing is setting up a basic crystallization experiment, which is a hanging drop vapor diffusion experiment. What it's doing is it's copying a deep well block, which has a commercial crystallization screen in it, to a crystallization plate, and then setting up a hanging drop, which is 200 nanoliters plus 200 nanoliters of protein and crystallization precipitate. So we can see the drops being set onto the cover slip. We have a crystallization tray there, large volume tips for transferring the screen, which is in the deep well block, and low volume tips for transferring both the protein and the screen conditions. During operation, the MT8 has an automatic humidification system, and this allows us to prevent sample evaporation and improve sample consistency. The MT8 software is fully customizable, where we're able to use any type of plate and make a definition for it, and modify our protocol list to do whatever liquid transfer handling that we choose to. Okay, next we'll talk about the RI1 Imager 1000. The RI1000 is a temperature-controlled incubator set to 20 degrees C. It can image any standard 96-volt plate, which has a SBS microplate footprint. Crystals can take days or weeks or even months to grow. So to maintain reproducible experimental conditions, plates are stored in a stable environment at a constant temperature. This allows us to get a permanent record of each drop as it develops over time. And now we'll take a look at the physical components of the RI1 Imager 1000. This is the Formulatrix RI1 Imager 1000. It's our automated imaging system. So here I'll go through the different components and the physical layout of our instrument. The imager itself is also a 20-degree temperature-controlled incubator. In the front here is the load port, where the plates get entered into the system. If I carefully open the door, this is the imaging stage where the plate would go, right on there. We also have the visible and the UV microscopes. If we look in here, you can see all the plate hotels. It holds up to 1,000 plates that are the 96-volt plate format. And down at the bottom, we see the two hands, which are responsible for moving the plates around the system. Also in the back, with the yellow sticker, we can see the barcode reader. There are two computers that control it. One computer controls the Rockmaker Software RI1 Imager, which runs the scheduling and also allows you to use the imager as a manually in microscope mode. The second computer runs the program Rockmaker, which allows you to design your experiments and look at your images and do much more. We'll get into that in much greater detail later. It has a barcode printer. We print out a unique barcode for each plate. And in addition to these two computers, there is a storage server connected to this that has all the images stored on it and backed up, as well as a web serving server that has Rockmaker Web on it, so you can work with your images remotely. So in addition to and complementary to our Rock Imager 1000, we also have a second imager, an RI1, which is an imager that is stored in a 4-degree cold box in the X-ray core. The functionality is essentially the same, except that it does not allow you to do scheduled imaging, as it only holds one plate at a time on the imager. It has visible and UV. What you would do is store your plates in the 4-degree cold box with the barcodes made by Rockmaker, and then once per day or whenever you like, come down, place them on the imager, and image the plate. Next, I'll discuss the software Rockmaker. It's a fully integrated crystallization imaging and experimental design and data management software that works in conjunction with the imagers and with the MT8 robot. Okay, so this is the software that's the user interface for the RI1000 imager. Software is called Rockmaker, and this is where you set up your experiments and program the automatic imaging. So let's look at making a new experiment first. So this is our new experiment window here. We'll give it a name. Got today's date, and we're going to do a Hampton index screen. You have to tell it what plate type it is. In this case, we're going to do a 3-drop sitting drop experiment. And then we're going to program it to tell it to image in visible light at 0 days and hours. And then in this sequence here, and we offset it by 12 hours. So most of the imaging occurs at night when no one's actually using it. We'll then set up a representation of your plate within the computer. So we have to add the well solution. We have all the commercial screens, and we can customize that however you like. Let's get index. And it populates it with the solutions that are in each well. Then we add our protein in. Just grab some protein here. Drop that into the drops. We're able to adjust our drop size here. And basically that's our experimental setup. So now let's look at an experiment that has been run for a while. This experiment here, this is a hanging drop experiment, more aggressive imaging schedule because I know this protein crystallizes faster. So if we look at the results, let's look at 3 days in Canvas. This is the overview of the canvas. So we can quickly look across the canvas, get an overview. We can see the scores in small letters. I'll get to the scores in a second. And then we can look at individual wells that look interesting. So we can look at each well on the plate, and we can scroll through the wells using the arrow buttons, like so. We can also go back in time and see how these crystals looked at the beginning, 0 hours, the next day. So these grew fairly quickly. And this will give you an indication of what time, how long they take to grow and mature completely. One advantage to that is sometimes crystals grow, they mature, and then they start to degrade. This way, if you miss the perfect time, you can go back and repeat it and know exactly when that is. We can also look at the UV imaging of the crystals. So this is taken in UV. And that's tryptophan, autotryptophan fluorescence, and this is definitely a protein crystal. A couple of tools we can use too. A ruler, useful to tell how big it's going to be when you mount it on the X-ray beam. Also to tell how much it's growing and consistency, and you can compare between drops and conditions of how large the crystals are getting. So that's the Rockmaker software pretty much. You program in what you're going to do ahead of time. It automatically images. There's also an automatic scoring system. Okay, the imaging software is also equipped with the Marco auto scoring algorithm. So Marco is machine recognition of crystallization outcomes. This is an automatic scoring system using AI to determine whether whether you have crystals, precipitant, or clear drops in each one of your drops. This method was published in PLOS ONE, and this is the reference if you'd like to follow up on it. This was done by a consortium of academic groups, folks at Google in their AI program, and private institutions. So basically the way that works in our system is every time your plate gets imaged, the Marco algorithm runs on it and scores it. Here we have the scores from that last plate of percent whether or not there's a crystal in that plate. This can greatly improve your observation of your plates, where if you're pressed for time, you can just look at the plates with high scores. What's also nice is that there's an email server built into the program, so it will email you if it finds what it thinks is a crystal every time it images a plate, which is nice because if you're very busy, you don't have time to look at your plates, or it's a plate that's been in there for a while and all of a sudden there's a crystal, it will tell you. So that's a nice feature. Next, I'd like to talk about using the MT8 to follow up on an initial crystallization hit. Typically, we screen a variety of sparse matrix screens to find an initial crystallization hit. Some folks at that point will take that initial crystallization hit and move to a classic 24-well plate. Now, this doesn't always work to reproduce that crystallization hit. And the reason for that is that if we look at the wells themselves, the physics of that vapor diffusion experiment is very different between the 96-well plate and the larger 24-well plates. So you don't often get that reproduction. So what does work to optimize that condition is continuing to use the MT8 and doing either a classic grid screen, an additive screen, seeding, an under oil experiment, or an iterative screen optimization, which I'll talk about more in a minute. In my hands, the first step of varying the drop volume and ratios has been a quite successful way following that initial hit. So what I mean by varying the drop volume and ratios is that the experimental setup is that initial hit from a 96-well block. We set up a tray where every well has that condition in it, and you don't have to use the material from the screen itself. You can use homemade reagents, or if you don't have that particular one, you can use something close, and that'll still provide enough vapor diffusion. And that variation gives us variation in the protein to precipitant ratio, surface to volume ratio, and the diffusion rate and total drop volume. So this chart shows an example of a concept ratio of what you can do across the 12 columns, where you vary both the protein and the precipitant, and that gives you a different total volume. And then here's an example of a result where we see in column 1 a reproduction of our small crystals we got in the initial hit, and then in some other columns an increase in size of crystal and a definite improvement. Next, I'd like to talk about a strategy called iterative screen optimization, or ISO. This strategy is particularly beneficial when working with a new target and when we encounter difficulty in obtaining an initial crystallization hit to follow up on, especially when using a suite of sparse matrix screens to begin with. So if we look at this famous graph of saturation zones, during a vapor diffusion experiment, varying the concentration of protein and precipitant hopefully can put us in the nucleation zone where crystals can form. So the strategy in ISO is to use the information from all the wells in the screen to create further conditions that will push the experimental conditions into the nucleation zone. In the past, this information was often used, and a screen with no histocrits was simply a dead end. So we started with a set of initial screens, and we'll focus here on an example of the classic Hampton index screen. Trays were set, and then on day 5, we have no crystals which diffracted well enough to collect data, and some of the initial hits, which were optimized in a traditional way, did not lead to success. So rather than going back to target construct design or in a different direction with additional space matrix screens, we can use this screen to continue. In the past, an initial screen with no crystal hits was not considered very useful, but there is data in the wells that do not have crystals there which can be utilized in an ISO process. ISO will allow us to move the crystallization environment towards a metastable supersaturated state where, although actual crystallization conditions cannot be determined prior, a cycle of scoring and screen improvements can be successful. So the first step is to observe the screen and manually score the conditions based on these 10 options, from clear up to actual crystals. Day 5 is typically chosen as the scoring day. So we do the manual scoring, and as a note, seamless integration between Marco and ISO is in development at Formulatrix, but is not implemented in Rockmaker yet. So one question is, why would we continue with ISO if we have some crystals? Well, perhaps they don't diffract, perhaps that hit won't optimize, and in a good case scenario, obtaining multiple conditions with different crystal forms, yet giving the same scientific outcome at the structural biology level, gives increased confidence to your scientific conclusion. So, after we score the entire plate manually, we have our grid of scores. And then in the Design tab, go to Optimization, set up an iterative screen. Next, and this gives the percent change values for each of the scores. And when we continue, that will produce a new screen with all our ingredients listed in it based on the original screen and our scores. So here's our new screen. So in theory, this is great, but we actually have to do the experiment in the lab. So several options are creating it yourself with the library reagents, either manually or preferably by using a microfluidic screen builder robot, such as the Formulator, also by Formulatrix, an instrument our core is considering as an investment, or an option more convenient and realistic currently is to take the screen, export it as an XML database file, and then we can send that to a commercial screen vendor and have it made, as they already have all the reagents and the screen building liquid handlers. So in my experience, Molecular Dimensions and Hampton will make the custom screen in a 96-well deep block for about the cost, 1.5 times the cost of a standard sparse matrix screen, and about a week turnaround. So then this process could continue. We would set the tray, incubate the tray, score it on day 5, do an optimization calculation, obtain the next screen, and so on until quality crystals are obtained. So you have to consider certainly purchasing these new ISO screens as an added cost. And it's certainly worth it to get the initial hit and pass the bottleneck in the crystallization pipeline. Additionally, this new screen is not limited to the particular target at hand. It can be used as its own sparse matrix screen for other targets in the future in your laboratory, thus expanding future screenings. Additionally, this method was proven on a smaller scale with 16 common low-cost reagents and published here. It's the same iterative concept, and this can be done with an MT8 Drop Setter, Imager, and the Rockmaker software. And this provides a lower cost in-house option to achieving crystals of stubborn proteins using the ISO concept. Membrane proteins are high-impact, very difficult targets, often requiring extensive screening and specialized crystallization conditions. LCP is often used as a medium for the protein. LCP is lipidic cubic phase, in which lipids form a repeating lattice of a bilayer. Reconstituted integral membrane proteins are able to diffuse and translocate through the bilayer as the LCP drop shrinks during vapor diffusion and come together to form crystals. The crux is that crystallization is dependent on diffusion. An LCP frap, which is fluorescence recovery after photobleaching, is a technique which measures that diffusion of the protein throughout the LCP bilayer in the drop. Essentially, prior to LCP reconstitution, the membrane protein is tagged with a Psi5 fluorescent dye. Crystallization experiments are using using glass plates, where a small drop of LCP is surrounded by precipitant and sealed by a cover slip. The MT8 is able to set LCP crystallization trays, and the RI1000 is equipped with a fluorescence module and accompanying software to perform the LCP FRAP experiment. So after some incubation, fluorescence is measured at a random spot in the LCP. That spot is then bleached with a laser. And then as the protein diffuses through the bilayer, the fluorescence signal is recovered in that spot, which is then measured. There are two basic ways to use FRAP. HT FRAP, or high throughput FRAP, where we can scan a sparse matrix screen of conditions that allows for diffusion with 2 time points 30 minutes apart. That gives us a raw value for percent recovery. And we get data produced like this that gives us some initial starting conditions. And then there's also full FRAP, where in a condition of interest, a single bleach spot is monitored for 30 minutes, and that gives us a rate of recovery as well as an interpolated total recovery, and that's shown here. Vadim Sherazov has pioneered much of the work with LCP, and his website is full of resources. This Methods of Enzymology paper is essentially the textbook on this technique, and this the manuscript of the structure of CCR5 is one of the many proven examples using this technique. The RI1000 imager can also be used for manual imaging. This is for creating high-quality visible and UV images and getting a better view and determining what's in the drop versus the automatic imaging. The automatic imaging is wonderful, but it has a fixed zoom, fixed drop location, and an autofocus. So here we have the imager on the left. This is a close-up view of the optics in the center, and on the right are all our manual imaging tool set. Okay, I can manually load a plate to the imager stage, and then once we've chosen a well, we can use our tool set on the side here to get a better look. So here's our well with our crystals in it, and we can double click and center on a crystal of interest. We can also zoom in. And once we're zoomed in and we have the crystal in focus, we can adjust the polarizer and also the focus level with the Z adjustment. And this will allow us to inspect and confirm this is a single crystal and doesn't have any cracks or imperfections. So working at zoom 7, once we have the crystal of interest in focus, we can also switch to UV mode and turn on the UV illumination and the live image, and then adjust our exposure and our gain. And at this point, if our crystal is protein, we'd expect to see autofluorescence of the tryptophan residues in the protein under the UV light. And this confirms that this crystal is indeed protein. Finally, I'd like to talk about Rockmaker Web. This is a browser-based interface which allows you to access your images remotely. Benefits of this include working from home or on the road when you have active trays in the incubator and imager. Several crystallography groups which use the core laboratory located across town on Science Hill campus, and this lets them view, design, and plan future experiments, and then only travel down to the core laboratory for either future experimental tray setup or harvesting of crystals for either diffraction experiments on our Rigaku home source or freezing them for shipment to a synchrotron beamline. And this ability to work remotely improves efficiency in your experiments, and of course now during COVID is even more valuable. So I'll briefly go through the features of Rockmaker Web. Visually, there's a slight difference of the interface than Rockmaker at the PC for the imager. So the features that are available are the ability to look at your entire canvas, complete with Marco scores. You can have multiple experiments open at once in different tabs. We can look at our drop and zoom in and move around the drop, complete with our measurement bar and the annotations that we can make. You can also view time course of the experiment. This was on day 2. See our initial time, day 1, and back to day 2. We can review our ingredients of the experiment and any experimental info we added at the beginning. We can also do the manual scoring remotely for record keeping or in designing our ISO experiments. And we have the option to manually re-image the plate using either the entire plate or the drops that we've marked interesting in either visible or one of the UV options. And this would be in addition to the originally planned schedule. So what Rockmaker Web cannot do remotely is design new experiments and create barcodes and work with the ISO design wizard. Of course, we can make accommodations for that through TeamViewer in certain cases, considering the importance of remote work. So in summary, the use of robotics and automation in protein X-ray crystallography has tremendous benefits. The crystallography core has modern robotic equipment. The MT8 Drop Setter can set any style of protein crystallization experiment. Rockmaker is a powerful software for data management and experimental optimization. And the imagers both provide high-quality images of experiments. The X-ray crystallography core is open to all Yale researchers and also outside research groups. And finally, for further information and resources, this is our core laboratory website, as well as my YouTube channel, which has a variety of videos on it, including a longer version of this webinar. Thank you.